Hi folks, this is Ramandeep Jindal. I'm here to present the peer graded assignment for managing machine learning projects. Let's look into our assignment. So we have to choose a problem in the field of our interest, work through series of steps to evaluate the opportunity, walk through the business understanding phase of CRISP TM, develop solution validation plan, consider key ML system design decisions, and then lastly, identify potential risks that may affect production models. Let's deep dive. So what's our problem and opportunity evaluation? So the problem we have selected for the project is handling real-time fraud in card transactions. This involves detecting fraudulent activities and preventing unauthorized transactions in real time. Let's take a deep dive further to even check whether there is even a problem. Yes, this is a genuine problem today within the financial industry as it's resulting in losses for both our customers and businesses. The companies have implemented traditional rule-based or heuristic systems that are not effective in detecting sophisticated fraud patterns. Now, can machine learning help solve it? Yes, machine learning models have capabilities to process and analyze large volumes of transaction data in real time and also identify complex patterns and anomalies. Hence, definitely machine learning models can help solve the problem. Does someone care even if we build a machine learning problem or solve this problem overall? Yes. Multiple entities like financial institutions, payment processors, customers have a vested interest in minimizing the fraud because it will lead to reduced financial losses, improved operational efficiency, and enhanced customer trust. Now let's look into the CRISP DM business understanding. Now, who are our target customers or the users here? Financial institutions, payment processors, and cardholders or customers, as we talked earlier. Problem we already defined. We want to handle real-time fraud in card transactions involving unauthorized use of stolen credit card information, identity theft, or payment ecosystem vulnerabilities. Now, does it really matter? I mean, when we try to solve this problem? It does because fraudulent transactions can lead to financial losses for both institutions and card members, loss of customer trust and the business to the institutions, and lastly, operational inefficiencies due to a lot of manual effort which is spent by the employees of the institutions to review the transactions. Now, what's happening in the current state? Uh, so most of the organizations have rule-based systems and manual reviews are commonly used, but all of these have limitations in detecting fraud patterns and adapting to evolving needs. From the success definition standpoint, let's look into the impacts of the work we're talking about. So firstly, what is the expected impact? Improved fraud detection and prevention in card transactions. What are the metrics? So from the outcome standpoint, we're looking into reduction in fraud losses, increased customer satisfaction, improved operational efficiencies. And what's the output? It can be MSE or R squared. From the target standpoint, if you look into the outcomes, we're looking into reduction in fraud losses by X%, let's say 60%, or increased customer satisfaction by Y%, for example, 80%, and improved operational efficiencies by Z%, and it can be, let's say, 70 to 80%. And output, when we say we're looking into defining MSE, which is less than XX or R scale less greater than YY. What are the constraints under which we are going to operate for this scenario? So there are going to be regulatory compliance, regulations and data privacy laws, which is the first biggest constraint. The second one is going to be the resource limitations because we're talking about a highly complex machine learning model, which will require high computational resourcing, processing power, or even storage capacity. And lastly, latency requirements, which is very, very important. We want to make sure that our machine learning model ensures timely fraud detection without causing significant delays in transaction processing. Very, very key for this kind of a use case because the transactions happen in milliseconds. And lastly, let's look into the factors. And this list is not sacrosanct, but yes, it's one of the representative list. So we are looking into transaction metadata like amount, location, time, cardholder information like their history, spend patterns, external data like device data, IP address, geolocation, etc. Transaction frequency, what is the size of transaction, for example. Transaction type, we want to make sure we understand whether the transaction was made online, whether it was on a point of sales terminal, or it was done internationally. What is the solution validation plan? So let's first look into what is the kind of machine learning model we're trying to work here. So we're looking to create or build a model which leverages supervised learning algorithms. And this model is going to be trained on labeled data set of historical transactions. We saw a list of those data elements in the previous slide. And from the validation approach standpoint, we'll be definitely running this entire validation through iterative experiments. Let's look into the various validation stages here. The first one being the pre-processing of the data, where we want to clean and pre-process the transaction data, handle missing values or outliers. We want to train the model using a labeled data set of historical transactions. We want to evaluate the model against the training set and the matrix we have set for, like, for example, MSE or R squared. And then we also want to compare the target of this model with the heuristics or the rule-based solution baseline. Very, very critical. And we want to then fine-tune the model by adjusting the hyperparameters or by feature engineering or by incorporating additional data. And then run cross-validations to validate the model on a separate data set to measure the performance. And finally, the real-time testing. We'll deploy the model to see as to how the model is performing and make any necessary amendments and repeat the process. And let's now jump to look into some of the design decisions when we are building this model based on three parameters. So let's look into our first choice, cloud versus edge. Now, for our use case, which is more of real-time detection of fraud, a cloud-based solution is going to be more suitable because cloud offers scalability, high computational power, and the ability to process large volumes of data. On the other side, when we look into the offline versus online learning, we'll prefer our model to be using online learning. Now, online learning enables continuous model updates based on real-time data, adapting to evolving fraud techniques and improved detection accuracy. And lastly, when it comes to predictions, whether we like batch or online, well, our model should definitely give online predictions because these will enable immediate analysis of transaction data and prompt intervention when fraudulent activities are detected. This is absolutely the key for this entire model. And lastly, let's look into the potential risks of the models which are in production. The first one is going to be the training serving skew. This is where we're talking about the model degradation due to significant difference in the distribution of real-time transaction data versus the historical training data. Uh, latency can lead to missed fraud alerts or negative impacts to the user experience. So we definitely need system with a very low latency here. Data drift and concept drift both can lead to several potential risks in production. Balance between false positive and negatives. So it's very important we strike the right balance between them because we want to minimize false positives. That's when we flag legitimate transactions as fraud, and false negatives where we fail to detect actual fraudulent transactions. Both are very risky on the other side, but we need to definitely make sure that we run through with a lot of edge cases when we test the model so that we don't fall prey to this problem. Attacks will increase and continue to increase because emerging technology, new technology, leaps which are happening in quantum computing, etc. This will all help attackers or fraudsters to manipulate ML models using very advanced techniques. So we need to constantly update our model to make sure we fix any exploits or vulnerabilities in it. Lastly, regulatory compliance. So compliance with relevant regulations and data privacy is absolutely critical. If we are not compliant, definitely we'll have a lot of issues and potential risks with this model. This brings us to the end of this presentation. Thank you for listening in. Goodbye.